Hello guys, welcome back to the Maths Club. This is Paul Ayub, your mathematics instructor. In my last video, which I posted on all my social media handles, I showed how we could use the knowledge of substitution to integrate a rational function. One of my subscribers on YouTube sent me another rational function question on integral calculus, and I discovered that that question is actually a Harvard University past entrance question in mathematics. So join me, ladies and gentlemen, and let's walk through the solution of the question that we have on the board. So we are given that evaluate the integral from 0 to 1 of ln 1 plus x all over x dx. Now, if you look at, I have circled in red this function in our integral. All the methods that I highlighted in the last video, like substitution, partial fraction, perfect square, and even recognition, they cannot go here because you cannot express the denominator as a partial fraction. You cannot express the denominator as a perfect square. You cannot express this. You cannot use substitution here. You cannot differentiate the denominator to give you the numerator so that we can use recognition. So those methods cannot work in this kind of question. So what do? We need to apply what we call the monotone series convergence method. Monotone series convergence method, where we are going to obtain the general term of this expansion of this series. So I will say consider ln 1 plus x all over x. So general term of ln 1 plus x. The general term of ln 1 plus x is actually the sum from n equal to 1 to infinity of negative 1 to the n plus 1 x to the n all on n. So if you expand this series ln of 1 plus x, the terms can be obtained using this general term. It implies for ln 1 plus x all over x, the general term will be the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 x to the n divided by n, all that divided by x, because I'm now having x in the denominator. So as I'm having x in the denominator, everything, this general term will be divided by x, and that is going to give us the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 x all over n times x. Because of indices, the power on this x is 1, the power on this other x is n, and since this x is in the denominator, so we are going to subtract the power from indices. It becomes n minus 1. So this will be the general term of this entire fraction. So we are going to be integrating the general term instead. That is the knowledge that we are going to apply. So it means this integral now becomes the integral from 0 to 1 of the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 all over n times x to the n minus 1 dx times n minus 1 times n minus 1 dx. So as you can see, this term is actually a constant. It is actually a constant, and a constant can always go behind the integral because the variable that we are integrating with respect to is x. So this guy is just a number. A number can go behind the integral. So that we now have the sum from n equal to 1 to infinity of negative 1 to the n plus 1 divided by n integral from 0 to 1 of x to the n minus 1 dx. So that gives us the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 all over n. When we integrate this guy, how do we integrate? You add 1 to the power all over the power plus 1. So this integral has to give us x to the n all over n, all that from 0 to 1. So that we now have this n can multiply with this n. So we have the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 all over this n multiplies with n gives us n squared into x to the n, all that from 0 to 1, which you can have as the sum from n equal to 1 right up to infinity of negative 1 to the n plus 1 all over n squared into, substitute your power, your limit. When you substitute 1 here, we are going to have 1 raised to the power n is 1 minus substitute 0 to the power n 0. So we now have this integral from n equal to 1 right up to infinity of negative 1 to the n plus 1 all over n squared, because this bracket will just give us 1. And when you look at this, value very well, this is a constant, and that constant is equal to pi squared all over 12, because it is the Riemann alternating zeta function. This is the Riemann alternating zeta function. It has a value of pi squared all over 12 at s equal to 2. So you also have the Riemann ordinary or simple zeta function, which has a value of pi squared all over 6. So this value comes from a theorem, the Riemann theorem, the Bernard Riemann theorem, who was a German mathematician. It comes from his theorem, and he developed this function and discovered that it has a value of pi squared over 12. So this integral is actually pi squared over 12. So if you want to know how to generate this value, how to obtain this value for the Riemann constant, comment in the comment section Riemann, and I will show you. So see you in my next video.